Hi, so today I'm going to look at redox titrations, and I'm particularly focused on the way that OCR in the A spec of chemistry do these questions. I've got another video about titrations, which is on the screen there, and it's all like the basics of titrations aimed at GCSE students. But if you're an A-level student and you find finding titrations difficult, it might not be a bad idea to skip over to that link down there and have a watch. Okay, so let's just run through some Chemistry 101. Okie dokie. Right, first of all, chemistry is about particles, yeah? That's actually what we're doing. We've got particles colliding. So when you write down an equation like A plus B and make some products, then what you're really thinking is, what that shows is what we think is that an A and a B collide. And a lot of the time they bounce off each other, because if you think those particles actually got electrons around them, so sometimes they actually bounce off each other, and that's where rates of reaction come into play. Because they've got to have enough energy to overlap of electrons to restructure themselves to make the products. But today I'm not interested in rate, I'm just interested in how the numbers work. So what we really need to be able to do for chemistry to work is count particles. Of course, that really isn't on. I don't think we can do that. What we can do though is we can count groups of particles. Okay, so we group them together. And one way to get your head on what we're doing here, because people find the idea of the mole, which is what we're talking about, find that quite difficult. But imagine you had a task like, for example, counting how many players there were in all the American football teams. They go on all the top ones anyway. Well, I suppose you could go around counting football players, but it'd be a heck of a lot easier if you find out how many are in a squad. I think it's 45 off the top of my head. I'm sure someone American or from the USA will be able to tell me. But instead of counting individual players, what we could just do is count how many teams there are. And then you'd multiply that by 45 or however many players there are in a squad. And that would be able to tell you how many players there are altogether. So we don't try and count individual particles, we count bunches of them. Fortunately, in chemistry, we've all agreed on the idea of the mole, which is a particular number of particles. So the group noun for particles, I guess, is a mole. It's just the same stem as the word molecule, so it's just a word. It just means a number. And yeah, it is Avogadro's constant. It's 6 times 10 to the 23. It's the exact number of particles. But to be honest, that doesn't really matter too much. All that matters is that for every group of particles in chemistry, when we say a mole, we mean the same number of particles. So when we want to figure out how many particles there are, how many moles there are of something, with solids, you can use a balance, and the mole is the relative mass weighed out in grams. So for example, let's see now, copper, I think its relative mass off the top of my head is 63 or 63.5. So if you weighed out 63.5 grams of copper, you'd have a mole of copper. Okay, you'd have a mole of copper particles. So I guess if we were going to pitch the copper against, let's go for chlorine, because I know that one, it's 35.5. If we're going to have some kind of crazy competition, you could get 35.5 grams of chlorine. Oh, wait a minute, it's a gas. Well, we'll come back to that one. But 35.5 grams of chlorine would give you a mole of chlorine. And that would mean that if you had a mole of copper and a mole of chlorine, you'd actually have the same numbers of particles for each one. As it turns out, that wouldn't quite work out, but we'll worry about that in another session. Okay, what else? We have solutions. So if you've got solutions in chemistry, then we use concentration to find out how many moles are swimming around inside the beaker. And the equation for that one is the concentration times the volume. And if we've got gases, we've even got a tool for working out how many particles of gas are bouncing around. And because gases are mostly empty space, the size of the particles doesn't matter too much. So a mole of gas occupies 24 litres or 24 decimeter cubed. Now there is an equation that we can use to deal with the fact if the gas isn't at 298 Kelvin in atmospheric pressure. That's that PV-nRT thing. But again, just the principle that we can use a tool to figure out how many particles there are of a gas. So titrations, well, what do you have? You have something in the bottom, an unknown number of moles. Yeah, sometimes the question dresses it up and it's actually what's in there has come from somewhere else, or it's a tenth of a sample of something bigger. But fundamentally, what you've got in the flask at the bottom is an unknown number of moles. You do need to be able to figure out or be told what the ratio is. Now what I mean there is that if I put 1 mole of chemical in from the burette, how many moles of stuff in the flask will it react with? Now a lot of the time that ratio is 1 to 1. So for example, if you're doing, I don't know, sodium hydroxide and hydrochloric acid, 1 mole of each reacts together. I've called it N here in this little problem because that would be a useful idea later. But just the idea of how many moles does 1 mole from the burette actually react with. Okay, and then what do? Well, you add a known number of moles, and you have a whole load of technique into doing a titration, but fundamentally you'll get a value at the end of how much of that solution you've added. You need to know when to stop, and that's where the indicator comes in. What that indicator is doing is telling you the end point. It's telling you when you reached equivalent, when there's no reactants left over. Okay, and yeah, to be fair, usually the indicator actually you notice just after that point, but the nature of titrations is that when you stop, you will actually find that there's a curve involved, especially with acid-base ones, and it doesn't matter too much if you don't get exactly on the value because the curve is very steep. So in this example here, if I've got 1 mole of whatever's in my magical burette and it happens to be reacting with n moles of stuff in the flask, and of course the balancing number in that equation is n. If I put 7 moles from the burette, then there'd be 7 n moles of whatever I'm looking for in the flask, and that's the basic principle of a titration. So, summary: titration, you need a couple of solutions that react, you need an indicator to tell you when the reaction is complete, and you need to know the ratio of the reaction, or how many moles of the unknown react with 1 mole of the solution you do know about, okay, which is in the burette. Well, there's no reason at all why acid and base, or acid and alkali, yeah, that's one combination, but there's no reason why you couldn't put a reducing agent down there in the flask that you don't know how many moles there are. And you need a solution that would react to the reducing agent, which will be an oxidizing agent. Okay, so if you stick an oxidizing agent in the burette, you can use the same technique of acid and base titrations to figure out how many moles of reducing agent are down there in the bottom. Now, the oxidizing agent that most people use, there are some of it like dichromate ions, but often we use manganate 7 ions, and they're called permanganate in Old English. Okay, so manganate 7 ions, and you can probably see one of the advantages of it straight away is that the fact the oxidation number is 7, the only way that number is going is down, so that number is going to reduce, which means that the permanganate is reduced. And of course, that's what happens to oxidizing agents. Yeah, when an oxidizing agent oxidizes something else, it has to get reduced. So a few points on that though, and you're expected to, certainly for A-level OCR, pretty much recall this equation, or certainly remember the key points. So potassium permanganate, well, the potassium is a spectator ion in this story, so we're not going to worry about that. We're just interested in the manganate 7 or the permanganate ions. Now, 1 manganate 7 ion does pick up 5 electrons, so potentially 1 mole from your burette could react with 5 moles of whatever's the unknown in the flask. Or it could be 2.5, I suppose, or it could even be 5/3 for feeling really mean to in the exam. A little bit of detail: the solution does need to be acidified. You see on the left there you've got 8 protons required to make this work, so there needs to be some acid around in there. Now sometimes the acid is actually swirling around in the flask because you've used acid to dissolve something. Sometimes the acid is actually in the permanganate. It's a little bit of detail. Usually we're not going to try and set you a trick question and not put the acid in there, so it wouldn't work at all. One of the beauties of potassium permanganate, or manganate 7 ions, is that it's self-indicating. The manganese 2 ions, they're colourless. So as soon as you see any pale pink from the manganate in the burette surviving, as you swirl, as soon as you see any pale pink surviving, you know that you've got some permanganate or manganate 7 ions have survived. So they're left over, so you've used up everything in the flask. So it's a self-indicating reaction. And another bonus, the manganese 2 ions also catalyse the reaction, so you can do it fairly quickly. As you're adding from the burette and swirling, you don't need to worry about the rate of reaction being too slow, because the manganese 2 ions that you generate catalyse the reaction. Okay, so let's have a quick look at an example. I call these blah 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 problems, so where I cut out all the unnecessary nonsense and just focus on what we need. So blah 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 blah, who knows what was going on? I think sometimes the blah 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 bit at the start of this is someone's got a spoon or a fork and they dissolve it in nitric acid because they want to find out how much iron's in it. I'm not really worried about that bit, I just want to focus on the core today. So we've got an unknown amount of iron 2 ions in the flask, and then we titrate it. Okay, and we use 22 centimeters cubed and 0.02 mole per decimeter cubed potassium permanganate. And so the obvious question is, how much iron is there? So let's get a pen fired up. Right, any titration problem, the very first thing you want to do, absolutely always, is going to be to work out how many moles you added from the burette. So N equals CV. Some people say you need to work out the equation first, but I'm a bit old-fashioned about this. I want to work out how many moles I've added from the burette. So the concentration is 0.02. The volume is 22. And it is centimeters cubed, and I've got to remember that little thing. But concentrations are given per decimeter cubed, but volumes in chemistry tend to be centimeters cubed. So 0.02 times 22 divided by 1,000, and my calculator turns out 4.4 times 10 to the negative 4 moles. Okay, and that's what I added from the burette. Now I do need to know how many moles the burette chemical, the permanganate, reacts with in the flask. I could probably guess because I've got the equation up at the top there, but I'm going to go through the whole procedure. Okay, because what we really should do, now if you're lucky they'll give you the overall equation, what we really should do is put that whole equation together. So what's going on in the flask? We've got iron 2, okay, and that is going to be oxidized to iron 3 and generate an electron in the process. Now I'm not writing in the states, but it's important in exams, certainly for redox, that you do put the state symbols in. I want to focus on the maths today. The other thing that's going on, the other half equation, is we've got our permanganate, and that's reacting with 8 protons and 5 electrons to give me manganese 2 ions and some water. Now when you write out the two half equations, what you do is much like simultaneous equations that you might remember doing if you did GCSE maths. Well, what you want to do is you need to get the sum coefficient the same, and it's the electrons we need to get the same. We've got 5 electrons down here in the second one. We've only got 1 on the top, so we need to times that whole top equation by 5. I'm going to put that underneath there. Okay, so I'm going to have 5 Fe2, and that's going to give me 5 Fe3 and 5 electrons. Okay, right, I'm going to cross through that now because I've used it. Right, now we just add them together. So 1 permanganate ion, and some protons and 5 electrons and 5 iron 2s. They're going to give me a manganese ion and some water and some iron 3, whoops, let's cross off there, and my 5 electrons. Okay, some students don't bother writing the electrons down, but it's good practice to put them in there, and then you can strike through them to show you've got it right. Okay, and we can see here that was the thing from the burette, and that's what's in the flask. So we can see that what's happening is the number of moles in the flask is 5 times the number of moles in the burette. 1 mole from the burette reacts with 5 moles in the flask. Okay, and we know how many moles were in the burette that we added from the burette. That was our 4.4 times 10 to the negative 4. So the number of moles of iron in the flask must be 5 times that. Okie dokie, so still got that on my calculator, fantastic. So times that by 5 and I get 2.2 times 10 to the negative 3 moles. Now that's how many moles of iron 2 ions were down in that flask. Now usually then you have to work backwards through the question and find out what was going on, and often those are iron 2 ions, and they'll have come from a piece of metallic iron that was maybe dissolved in some nitric acid or something like that. But the key thing, of course, is if you've got that many moles of ions, okay, of ions, then they came from the same number of moles of iron atoms. So you'd be able to work out the mass of iron that all came from. But that was individual to the question. Okay, but basically the core here we've got out now. If you had to turn it into a mass, the molar mass of iron is 56, the relative mass of iron is 56. So that's 56 grams per mole. So if I times that by 56, that will tell me that there was 0.1232 grams of iron involved at the start of the story. Okay, that is the end of part 1. I'm going to have a little break and I'm going to come back and do part 2.